V2 for the reverse biased diodes under the drain and source region. And regarding this capacitance, we have studied a lot. Okay, so we can go ahead without further discussion on this. And this capacitance is the main parasitic capacitance which has to be reduced if we want to reduce the CL, load capacitance connected at the output node. As such, it is not connected, it is intrinsic capacitance, right? But sometimes we show explicitly for describing the propagation delay or power consumption, etc. when we describe inverter. So many times we have discussed, so let me go ahead and see other things. Another capacitance component of CL is line capacitance or wiring capacitance, which we call also interconnect capacitance, the capacitance from this output node to the input node, line capacitance. Then gate capacitance of Fanout gate, CG3, CG4. In this case, these two capacitances, as you can see. So all the capacitance involved or all the capacitances that contribute to CL, actually CL as such not existing itself, it is due to these capacitances. So Fanout gate capacitance is C Fanout is C gate of NMOS, I mean this one CG3, and C gate of PMOS. If you look at all the components of C gate and MOS, then CGSO and MOSFETs gate to source overlap capacitance and gate to drain overlap capacitance and COX multiplied by area, WN into LN is nothing but the area of the gate. Similarly, this part is for MOSFETs. Okay. See Fanout, we normally used to say that one of the component of CL is COX of Fanout gate, COX of Fanout gates and two COX. But I mean to say, I might have said only this part. But yes, if it is not a self-aligned process, then these two component also will be there. But nowadays, CMOS processes are self-aligned, so overlap is negligible. So this capacitance can be neglected. These two capacitances. So basically, it will remain COX, and of course, it has to be multiplied by area because COX is expressed as farad per meter square or centimeter square or micrometer square, right? So this is the component, another component of load capacitance. Now another thing what is very important is Miller effect. What is I mean this capacitance, if you use, I mean if you consider, then twice of this value has to be connected here with the ground, twice of this CGT. That I have already discussed, twice of this value because of the Miller effect. It assumes that all components of the gate capacitance are connected between Vout and BD or ground and ignores the Miller effect on the gate drain capacitance. This has a relatively minor effect on the accuracy, since we can safely assume that the connecting gate does not switch before this, it is talking about these capacitances, all these capacitances. These capacitances are floating, not connected, one end not connected to ground. So you can consider Miller effect here. This part we have already considered earlier in the last lecture. So actually we should use Miller effect and then find it, but it is not so necessary, because we can assume that when it is the CL is the voltage across this CL is changing, possibly it is not changing that much immediately. So that's why we can ignore it, since we can safely assume that the connecting gate, means this second gate, does not switch before the 50% point is reached. The Vout 2, this Vout 2, therefore remains constant in the interval of interest. When it is raising up to 50% point, for example, or falling 50% point, then possibly this Vout 2 is not changing or remaining almost constant. So we can, I mean, ignore that much accuracy and then do the computation. The computing capacitances, here we have already seen that when your gate voltage approaches threshold voltage, the capacitance is minimum. And when it is off or in saturation regions, or you can think of here also, when VDS by VS minus VT, this ratio is 1, means it is the MOSFET is in saturation region, then the whole, capacitance value CGS equals to two-third of COX into WL. This thing we have discussed, so we'll just go ahead without spending more time. Is all we have discussed. Now, a little bit about, of course, it was discussed in analog circuits, but here once again the Miller effect, effect of CGS and CGD, CGD1 of this MOSFET Q1 and CGD2 of the MOSFET. So these two capacitances of these two MOSFETs are floating capacitances, and we can convert into, say, grounded capacitance. For that, what has to be done is here, okay, the gate drain overlap capacitance of Q1 CD1 can be replaced by an equivalent capacitance between the output node and the ground with double value 2 CGD1. The factor 2 arises because the Miller effect, because of the Miller effect. Specifically, refer this figure and note that V1, VI or input voltage, VI goes high and VO goes low by the same amount, and VO means this one. The change in the voltage across CGD1 is twice that of that amount. Thus, the output node sees in effect twice the value of CGD2. So it has to be multiplied by 2. This factor 2 is coming because of that. The same applies for the gate drain overlap, this one, for this one also, okay, which can be replaced by capacitance this one. This is the here why it is to be, once it is increasing, here the value across this capacitance will be decreasing, so twice value will be connected here. In this diagram it is shown the same thing. So the second inverter does not switch states. We will assume that the input capacitances of Q3, Q4, this, talking about these two, of Q3 and Q4 remain approximately constant and equal to the total gate capacitance. That is, input capacitance of the load inverter will be this expression. This expression actually here. The last component of C is the bearing capacitance that we have seen in the last. This total value of C is given by this expression. I mean, if you consider all the capacitances, then this is the equation. I mean, load capacitance equation. 2 CGD1, 2 CGD2, and this is for say N MOSFET, this is for P MOSFET. C dB1, C dB2, that is drain to body of N MOSFET, drain to body of P MOSFET. CG3, CG4, and wire capacitance. This is, of course, if you consider the self-aligned process, we are not considering here overlap. Okay, so this is what the load capacitance. And here again, little bit highlight has been given. If it is a capacitance or inductance or resistance, if it is a floating capacitance or resistance or inductance, then this can be used as a grounded capacitance between these two nodes as shown here. Okay, Z1 and Z2, and Z1 value will be Z by 1 minus K, and Z2 equals to Z by 1 minus 1 upon K, where K is the gain, V2 by V1. V2 is this one, V1 is this one. Okay, similarly, in case of other circuits, maybe amplifier or something, and they are also same way. A floating capacitance can be used as a grounded capacitance, and in the two terminal we can connect it. We can review this topic if you are not following properly. So now we'll talk about the propagation delay. This is the next topic we have to understand. TP, normally denoted by TP. TP is the average value of TP-HL and TP-LH. See, 50% point of input, 50% point of input. See, input is rising here, D in is rising here, and what will happen? Your output will fall. So when output is falling from high to low, so up to its 50% point, this time duration or delay is called TP-HL, because output is moving from high to low value. So that is TP-HL. Similarly, when your input is falling, output will be rising. So from this point, 50% point of input to the 50% point of output, this delay is called TP-LH, low to high. Input, output, low to high. With reference to output only, remember this. This is with reference to output. Output when moving from low to high, so that is TP-LH. The average of this is called TP. Now tell me, if you want to have TP-HL equals to TP-LH, TP-HL equals to TP-LH, what is needed? How you will design the inverter so that it will become this? And it is really, ideally it is required. Both should be equal. How we can design or think of designing this? Somebody tell. Prem Prabhat, are you there? Prem Prabhat is absent.
Okay. Charging and discharging happens at same. It takes same amount of time to charge and discharge and
when it will happen? When it will happen? That is the question. Charging and discharging, if it's happening in the same time, then that will happen. But when, how your MOSFETs will be designed or sized so that it will happen?
Sir, when switching threshold is exactly VDD by 2.
Yes, you are there. You are Shashank or
Yes, sir. Yes, sir.
Shashank? Good. So when Vm is VD by 2, okay, and for Vm equals to VD by 2 at 250 nanometer technology generation, what should be the size of the MOSFET? Tell me. Hmm. What should be the size that we have discussed and you might have understood also? Hmm. We have discussed and you have understood. Hmm. Tell. Harsh Tripathi, tell.
Sir, the ratio WP by WH should be 3.4.
Yes, very good. See, I observed that you didn't attend classes. I am not really. I consider you one of the good student in this batch. Hmm? Any health issue? Why you are?
No, sir, not.
Why you are joining at 9 o'clock and doing this? It is not expected from the good students. At least these 7 students I am calling. Hmm, I don't expect from you. You should be the most knowledgeable students in this domain. Okay. Anyway, let me go ahead. I observe you. Okay, you 7. Okay, because there is no excuse for you. Excuse in the sense, once some company is coming, Vlsi company for recruiting their staff, they will not uh, consider that you are not knowing. You are supposed to know everything. Okay, and then priority also will be given to you. No, priority also will be given. Expectation will be more on you. Anyway, let us go ahead. So I hope you understood what is the TP. I will go ahead. What I wanted to say is also answered by Shashank and Harsh Tripathi. DM should be VD by 2. For that, you have to properly size the NMOS and PMOS fit. Sizing means if you take the channel length same, you have to manipulate the width, mainly of the PMOS fit, because that is basically weak compared to NMOS fit because of what? Because of what? Himanshu? Mobility. Mobility. Good. Hmm. So no further discussion on this. Now, the uncertainty over when a transition actually starts or ends is avoided by defining the rise and fall times. Another two terminologies coming, rise time and fall time. Okay. So between the 10% and 90% points of the waveforms, as shown here. Okay. Yeah, 10% to 90% point. Hmm. So the rise or fall time of a signal is largely determined by the strength of the driving gate and the load capacitance. Driving gate means from where input signal is coming, and the load capacitance, its value. Okay, its value, you know, everything is known to you. What are the various components of CL? See, rise time and fall time. I mean, from rise time 10% to 80%. How much time the signal is taking? Okay, and or when from 10% to 90% to now 10% when the output is falling. That is called fall time. This definition of rise time, fall time is here, but in other books you may get 20% to 80% also. Okay, so don't be surprised. More or less, this is the we are referring Janem Brave's book, so refer this one. I mean, once you are asked in the exam or viva, you say that it is 90 to 10%. In West it will find 20 to 80. The digital circuits are often modeled as first order RC networks of the type shown here. The propagation delay of such a network is of the considerable interest, and V out T dependent can be written as 1 minus e to the power minus T by RC into V in. Okay, which we can write as 1 minus e to the power minus T by RC equals to V out by V in. Okay, and V in is going to be VDD, okay, generally. And to complete the time to reach 10%, VD is 10%, 0.1 VDD, okay. So what we get here is ultimately T equals to 0.105 RC, okay, to raise, or the time required to 10% rise is 0.105 RC if you calculate this way. Similarly, if you want to see how much time is required to output or input to rise, mainly we are concerned with how much, to 50% raise, how much time is required? It is 0.693 RC. Is it understood from this equation?
Yes, sir.
Yes, sir.
Suppose you want to see the rise time in 10 to 90% point is also important. For that, if you see that T equals to 2/3 RC, 2.3 RC. Okay. So if CL value is more, this time required to raise up to 90% or 50% will be more. Okay. See, delay depends on this RC value. C means here your CL mainly. And R means what? What will be R here? We consider an inverter and we want to find out how much time it will require. How much time it will require to raise up to 50% point or 90% point. Till it is raising 90%, we cannot say that our output is high. Okay. Or till it is falling up to 10%, we cannot say that our output is low. Okay. So how much time is required to raise our output to rise our output to 90%? Then we are sure, yes, our output has gone high. If you raise 50%, possibly the gate which has to be driven by this gate cannot understand it as a high value. Okay, because in the interconnect there will be noise also. If that noise goes in a negative direction, then it may be difficult. Suppose in a 1 volt system, it is raising up to, supposed to raise up to, you study only, you have discussed, you have inverter, okay, and your input is constantly changing and output is taking some time. T equals to, what is that value? 50% point is 0.693 RC. 0.693 RC. And it is not able to rise fully. This is the full value. Rising up to here. It was low. And before that, your output is again going high. Then it will fall. This value, 50% point, say 0.5 volt, and negative spike has occurred. So it may further reduce and it may become 0.3 volt. If the negative spike here is say 0.2 volt, so this cannot be considered as high by this second inverter. That is what we have discussed in the last class. So the value R and C, how important you can understand. Circuits may start malfunctioning if you do not lower the transition frequency or input frequency. In other words, before your output rising fully, suppose input is changed, then this may happen. The circuit speed depends on the RC value. What is the meaning of R here? Tell me, at least we are talking about inverter, you must be able to say. Say somebody, Himanshu, at least for the case of inverter, tell what may be the
sheet resistance.
Sheet resistance.
Say, I am telling that output is rising. So tell what actually I am telling here for this R. Output is rising at this point I am telling. Tell when is output is rising of this first gate, first inverter, second inverter, and this discussion is going to say R and C. C, you understood that it is a load capacitance, but what is R here?
There is the sheet resistance.
Harsh Tripathi.
Sir, resistance of PMOS and NMOS.
Yes, you are there. It is the resistance of PMOSFET here. And we have seen that resistance, MOSFETs are modeled as resistance, finite resistance in on state. And in offset, it may be considered as infinite. So this RP, while charging or when output is rising, when output will be falling, okay, when output will be falling, this point is falling, then Rn. Understood? So resistance of MOSFET and PMOSFET can be varied. How? Tell. See, Harsipat, you be more active because I need this kind of student in the class. In the previous batch, when I used to teach, I'll be asking here and there many students. And ultimately, I used to get proper answer, mostly, not always, from Utkarsh Srivastava, one senior boy. He used to understand. He used to understand what I am asking. So that quality is there in you, Harsh Tripathi. Okay. But I saw that in the beginning you were absent because of your corona. Now also I find sometimes you are not joining the class. So if you are not, think of, okay? I consider you, yes, tell.
Sir, W by L ratio, sir.
Yes, you are correct. You have to increase its width, okay? You have to make MOSFET stronger. But which you are is either NMOSFET or PMOSFET. Keeping length same, you don't increase the length. Increase length means increasing resistance. You want to make stronger MOSFET means you have to reduce its resistance. So make it wider. Okay? It is like wire. If it is a wire having larger diameter, will be having less resistance. Same thing here also. Going further, the same thing TP can be also computed in this way. So, and RPRN again coming here. Whatever I was talking is here. So I'm just keeping. If you are taking the snapshot, take it. I'm going ahead. Then equivalent resistance, how it can be calculated with the current equation is given here. So see that. And whatever I was telling is 0.693 and equivalent resistance. of N MOSFET or P MOSFET is already we have discussed with that equation. And TP finally is given. It is considered 50% point. So I think you can understand that it was 693 I was telling. So we are also defining this 50% point things. Okay, TPHL and TPLS from 50% point to 50% point of output. So it is this okay. The definitions are all discussed. Go ahead. Some interesting design considerations and trade-offs can be derived from the delay expressions. Let us see what author is telling. By consistently widening the PMOS transistor, its resistance can be matched with that of the pull-down NMOS device. That is the way, so that you can bring VM equal to VD by 2. Already somebody has answered, I think Shashank. This typically requires a ratio of 3 to 3.5. As Tripathi said, it is 3 point what? 4 between NMOS and PMOSFET in this technology generation. Now, the motivation behind this approach is to create an inverter with a symmetrical VTC and to equate TPHN and TPLS. All these things we are discussing only. However, this does not signify this ratio. This ratio is the minimum TP. See, so this author is so nice. He critically analyzed each and everything. Why he is telling this statement? Can somebody tell? See, once you are increasing the width of the MOSFET to match up the NMOSFET strength or current driving capacity. Okay. What may happen is you are going to increase the drain diffusion capacitance of which MOSFET?
P MOSFET.
P MOSFET. So that is the part of CL. Okay. And CL is increasing, then what will happen? TP is going to increase. Charging time will be more. So that is what he is mentioning here. If symmetry and reduced noise margins are not of prime concern, it is actually possible to speed up the inverter by reducing the width of the PMOS device. Okay, not necessary that you have to maintain VM, and then it is only when symmetrical rise time, fall time, or TPH or TPLS is required. If it is not necessary, then possibly you not to wide the P MOSFET up to 3.4 times. Okay. So ratio need not be that much. Before that, possibly you will be able to achieve the propagation delay, minimum propagation delay. Okay. Something related to this we'll discuss. See that TP, if you, this x-axis is beta. Beta we know. The propagation delay of CMOS inverter as a function of the PMOS/NMOS transistor ratio. Beta. Beta is defined here as W by L of P MOSFET divided by W by L of N MOSFET. Okay. If you increase the beta in the x-axis and y-axis is your TP, what is happening? TP increasing this ratio, TPLH is decreasing, whereas TPHL is increasing. And a crossover point will be there where you will get the minimum TP. Okay, minimum TP. But see that actually it is here. The graph clearly illustrates how a changing beta trades off between TP-LH and TP-H. The optimum point occurs around beta equals to 1.9, possibly here, which is somewhat higher than predicted. Observe also that the rising and falling delays are identical at the predicted point of beta equals to 2.4. I hope it is understood. In this analysis, we assume symmetrical inverter. This is an inverter, and this analysis is done, this plot is done considering a symmetrical inverter. This is an inverter where PMOS and NMOS are sized such that rise and fall delays are identical. The load capacity of the inverter can be divided into an intrinsic and extrinsic component. CL, intrinsic and extrinsic component. Okay. So intrinsic part is what? This one, maybe the diffusion, drain diffusion capacitance. Extrinsic may be your fan-out gate, wear capacitance and fan-out gate capacitance. That is what? That is C ox into WL. This part is this one, gate capacitance of fan-out gate, and wear capacitance W. This is extrinsic, and intrinsic is your drain diffusion capacitance or the effect of CGD of both the P MOSFETs, Miller effect. C in represents the self-loading or intrinsic output capacitance of the inverter and is associated with diffusion capacitance of the NMOS and PMOS transistors as well as the gate drain overlap capacitance. Overlap capacitance can be ignored if self-aligned process is used. The C external is the extrinsic load capacitance attributed to fan-out and wearing capacitance. Is it difficult to understand, Prajwal?
No, sir, we already know this.
Read all are known to you. These all are known to you. See that? You take the snapshot. I want to go ahead and finish it up quickly. Okay. This all we have seen how it can be done. So please read yourself. Many students are not joining, participating, and they want to read. So let them do it. Okay. So sizing up inverters, how to size it. As you can see that if you keep on widening the MOSFET to make VM equals to VD by 2, maybe sometimes increasing the TP, even for that value 3.4, you may get the lower TP or lowest TP. So we find from this table that C in by C external, internal by external equals to 1.05. C internal is equal to 3.0 femtofarad and C external is equal to 0.1 femtofarad. Can you see here? This would predict a maximum performance gain of 2.05. A scaling factor of 10 allows us to get within 10% of this optimal performance. And while larger device sizes only yield ignorable performance gains, too much gain may not be available. So this may be given in an example. Might have been given in example 5.7 device. I mean this in this example, okay, device sizing, and this table is also given in the book. Go through. I am hoping that you all have the books. You have downloaded the books, and calculations I have done in such a way that you can understand. Maybe something is given in the book like this table, but everything is not. So I have calculated all and put here. You see this. Now, this is confirmed by simulation results which predict a maximum obtainable performance improvement of 1.9, that is TP0 equals to 1.19.3 picoseconds. From the graph of this figure, we observe that the bulk of the improvement is already obtained for h equals to 5, and that sizing factors larger than 10 are barely yield any extra gain. While sizing off an inverter reduces its delay, it also increases its input capacitance. What does it mean?
Drain diffusion capacitance increases.
Other thing, no, here telling input capacitance.
The gate to drain.
Hmm?
NGD.
It is telling if you are, say, you are not designing only one inverter. In a system, multiple inverters, multiple gates, NAND gate, OR gates, etc. Everywhere you are supposed to reduce the propagation delay. We are taking as a example of inverter, but that is representative for NAND gate, NOR gate, OR gate, etc., etc. Everywhere we have to optimize the delay. Then only circuit performance will be improved. Okay. So you should not think only about your gate. What about the gate which will be driven by your gate? If W width of a MOSFET is increased in a system, what is going to happen? Are you not going to increase the capacitance C aux into WL of the other gate also? In a system, you are not going to see, you are thinking about your gate. This is your gate. You want to reduce the TP of this gate. So you are increasing the W. Okay, you want to reduce the TP, you want to increase the W. But once you are increase the W, what about its C aux, which is the another inverter is there, for example, is going to drive it. What about this one? Is it not increasing? This W is going to increase the C aux. For this gate, are you not increasing the input capacitance? So its CL will be increased because of this wider MOSFET here. Is it understood? What it is the meaning of input
Yes, sir.
capacitance? Hmm?
Yes, sir.
The meaning of input capacitance. Okay, once you are properly sizing to get minimum TP, you are doing increasing W of this gate, but you are creating problem for other gate from which input is coming. Is it understood? Himanshu Shogra.
Yes, I understood.
Then I can go fast. To determine the input loading effect. So it is something like input loading effect. The relationship between the input gate capacitance CG and the intrinsic output capacitance of the inverter has to be established. Both are proportional to the gate size. So this is the beauty of this book. Understood? He he doesn't leave anything. Whether multiple authors are there, we should say, they don't leave anything. Everything is analyzed properly. That's why this book is so popular for digital design. Hence, the following relationship holds independent of gate sizing. C int gamma CG. C int equals to gamma CG. Gamma is the proportionality factor, which is only a function of technology and is close to 1 for most submicron processes. Writing this equation, we can write Tp equals to Tp0 within parenthesis 1 plus C external by gamma Cg equals to Tp0 1 plus F by gamma. This shows that the delay, if the inverter is only a function of the ratio between its external load capacitance, and input capacitance. External load capacitance and input capacitance. This ratio is called the effective Fanout F. This ratio is called effective Fanout F. So these definitions will be used in future also. So try to take this snapshot, understand what we are discussing. Discuss the impact of introducing this topic. I am not covering propagation delay from a perspective. Little bit discussion is there. Read it yourself. Discuss the impact of introducing buffer stages for a variety of values of F. Overall effective fan out of the circuit. Provide an in-depth discussion on the rise time, fall time of the signal. These are the possible questions from this area of propagation delay. Provide an in-depth discussion on the delay in the presence of long interconnect wires. So little discussion is left over for you in this topic 5.4.3 dynamic behavior of inverter. One small topic I might have not included here. So now power, energy, and energy delay product. Those things has to be covered from chapter number 5.5 of J&M Ravi. So far, we have seen that the static CMOS inverter with its almost ideal VTC, symmetrical shape, full logic swing, and high noise margins offers a superior robustness. Another major attractor for static CMOS is the almost complete absence of power consumption in steady state operation. Why there is no power consumption in steady state? If you ignore the leakage current, tell me somebody. Because only one network, pull down or pull up, is on at a time, not both. Unlike pseudo-NMOS logic, isn't it? Static power dissipation. Static condition means what? Static power dissipation or your steady state condition or operation. What do you mean by that? Input is held high and remaining high, or input is held low or remaining low. Say, consider the case of inverter only. During this steady state condition of inputs, output is not going to make any transition. Output is not making transition means your CL is not going to get charged or discharged. So there is no dynamic power consumption. And you know that in steady state condition, either pull-up network or pull-down network is on, not both at a time. So there is no direct connection from VDD to ground. So there is no possibility of static power consumption. Okay. But no, there are leakage in today's small size MOSFET. So leakage will be there. If you ignore the leakage, then there is no steady state conditions, power consumption will be there. It is this combination of robustness and low static power that has made static CMOS the technology of choice of most contemporary digital designs. The power dissipation of CMOS circuit is instead dominated by the dynamic dissipation resulting from the charging and discharging capacitance. This is all known to you, so we should go fast. Dynamic dissipation due to charging and discharging, this all discussed. So equation will be coming, and that you should remember. So charging, I see, is going to charge, P MOSFET is going to charge CL. That is being said here. Dynamic participation. So simple. But yes, mathematics is there. Here you should understand this mathematics a little bit. Dynamic participation, the values of the energy E VDD taken from the VDD during 0 to 1 transition, 0 to 1 transition, as well as the energy EC stored on the capacitor at the end of the transition. 0 to 1 transition of what? Input or output? Tell. Measure the energy EC stored on the capacitor at the end of the transition. So what transition it is? 0 to 1 transition of input or of output?
Output.
Output, obviously output. Okay, you can understand from here. Stored energy in the capacitor. Capacitor is nothing but your CL. Can be derived by integrating the instantaneous power VD into I of T dependent, time dependent. Remember that MOSFETs are going to change from cutoff to linear to saturation. Okay, this kind of change occurs. So every region is having different current passing through it. And currents are not constant, so it is IT dependent over the period of interest. So it has been done here. The energy E VDD taken from VDD during the 0 to 1 transition can be written E VDD equals to integration of VD IC within parenthesis T dt from 0 to infinite. And after this mathematical manipulation, you get the value of EC, okay, equals to this. Ultimately, this is the equation you get. CL VD square by 2. The corresponding waveforms of Vout and IVD are pictured in this figure. Vout is rising like this while charging, and IVD is going to be initially very high, okay, then it will be falling. As the capacitor is getting charged, the current will reduce. Initially, it will be charging with very high current, then the current will be reduced. That's what is shown here. And this part is discharging part when N MOSFET is on. So these results can also be derived by observing that during the low to high transition, the CL is loaded with a charge CLVD. Providing this charge requires an energy from this supply equal to CLVD square equals to Q into VD. The energy stored on the capacitor equals CLVD square by 2. This means that the only half of the energy supplied by the power source is stored on CL, where other parts goes. Other 50% or half energy is dissipated in the P MOSFET as heat. Okay, when current is flowing through a resistance, RP is the resistance. Definitely, it will be heated up, and energy will be dissipated there. So during the discharge phase, the charge is removed from the capacitor, and it is. Somebody is telling something?
Sir, we have another class going on right now.
Next, you tell in time, okay? Next class. You should not be late in other classes. As I don't want, you should be late. That teacher also can be explaining the same thing. So with this, we are ending. So plan for, I am today at 225 to 24 slides. Another day will be required to complete. So plan for the, which one? Tell me the time and date. Okay, leave the class and join
So
the
again,
classes.
I think 8 a.m. is the best time
Huh?
even for
Tell
extra class.
time
8 a.m. on any day will be the best time because we are
for
basically
exam. No, see, normally
not exam.
I suggest the timing for exam is on Saturday and timing maybe in the evening, because I want that you should be reading the things and give the exam so that you score 10 on 10. Okay. So my suggestion, as earlier also you might be with me, not on the class time. It should be on the evening time other than class timing. Evening time I give because possibly you will be getting the whole day to read, and that too if it is in Saturday or Sunday. Sunday is most preferable because you get Saturday as well as Sunday. Okay, but for exam classes will not be disturbed. It will be on. So decide Saturday or Sunday as per my suggestion. Otherwise, you discuss and decide and tell me. Okay then. Chalo, bye.